My name is Joe Cresco. I'm the Chief Engineer in the Industrial Efficiency and Decarbonization Office. I'd like to thank Martin for his discussion. The moment is important. The UN climate report came out yesterday, highlighting the imperative of change, and identifying how even small perturbations on our economic systems, the way we live on this earth, are dramatically impacting the climate, even more than we expected. Our projections for impacts have been underestimated for a long period of time. We keep seeing the urgency of this, and that moment is particularly important. And with that, this is really a great honor for me to be able to introduce Doyne Farmer. I first met Doyne about 12, 13 years ago, where Doyne had been leading a summer study, a global sustainability summer school at the Santa Fe Institute, and I found that to be one of the most impactful and sort of life-altering experiences of my life. And I think as we're thinking about the fact that we need to really improve and change this technosphere and the way we live with the biosphere, this is a complex system. It's a very dynamical and complex system, and I can think of no one better to talk about sort of complex systems than Doyne. Doyne is the Director of Complexity Economics Program at the Institute of New Economic Thinking at the Oxford Martin School and Baillie Gifford Professor of Mathematics at the University of Oxford. He's also an external professor at the Santa Fe Institute, and his current research is in economics, including agent-based modeling, financial instability, and technological progress. With that, I'd like to introduce Dr. Farmer.
Pleasure to be here. Let me make sure I understand how to advance the slides. Here we go. So it's a pleasure to be here. Yesterday, and by the way, I'm going to try and finish a bit early so that you can ask me questions. So think of your questions, because that's always more fun. But I want to begin by referencing back to yesterday, Sally Benson's talk. I gave her a little bit of flack about her technology investment agenda, and she responded by saying, quoting George Box, famous statistician, saying all models are wrong, some models are useful. The problem is most models in economics are not useful. And you have to be particularly careful if you have models that make predictions and you have no idea whether those predictions are any good, as we'll see a lot of them are not any good. This is an example of a forecast of the IEA for solar photovoltaic prices. And what you see, the forecasts and those colors over 2 decades versus what actually happened, you can see right from the beginning the forecasts were way off. They persisted in being way off for 2 decades, and they never, they incrementally changed them, but never really made up the difference. And this is sort of true across the board in the whole economics of climate change, that we've been living with models that have been making bad forecasts for a long time. In addition to making bad forecasts about solar costs, they also made bad forecasts about solar deployment, far, far too pessimistic about relative to what happened. Okay, I also made a forecast in 2010, published in Nature, about the future price of solar power in 2020. At the time, this was viewed as a crazy forecast, but it turned out to be pretty close to right, namely that we would hit parity with coal-fired electricity and nuclear power by 2020. And so in this my presentation today, I'm going to review work we've done on trying to forecast what will happen in the energy transition. Energy makes about 75% of carbon emissions, so if we change the energy system, we've solved 3/4 of the problem. And the punchline, which I hope will come through loud and clear, is that we can make the green energy transition quickly and at a purely economic profit with high likelihood. And then I'll talk about what we need to do that. Now, a lot of my message is contained in this. Let me see if I have well, it doesn't really matter. Oh wait, here we go. Is contained in this plot, which gives the evolution of the world's energy supply over the last 140 years. And if starting with a plot on the right, We see up at the top in 1880, we at the time, traditional biomass was tied with coal for producing supplying energy. Coal took off, and notice this is a logarithmic scale, so each one of these ticks is a factor of 10. Coal takes off and becomes a dominant energy source. We see oil and natural gas rising until they rival coal. We see, down here we see hydropower, nuclear power, and then down here we see renewable, what I'm going to call the key renewable technologies, solar energy, wind, batteries, and hydrogen-based fuels, and we see them all rocketing up on this scale, increasing in deployment by factors of 30% or so per year. Now, if you go over on the left side, you see, for example, this dashed brown line, which is coal-fired, or that's coal, primary coal. And one of the things that strikes you right away is over a 140-year period, once you adjust for inflation, coal costs a very similar amount now to what it did 140 years ago. Similarly, oil costs a similar amount to what it did. It's a bit more expensive, but not dramatically so. We see nuclear power coming up in price. This is US nuclear power by about a factor of 3. Globally, a few countries have declined a little bit, but not much. So staying roughly constant. In contrast, you see solar energy dropping very strongly here. And you see that we're in a very unique situation right now because we have a variety of different energy sources, all in a similar cost zone, all competing with each other for dominance. So now what I'm going to talk now that's relevant also for circular economy, though most of my talk is going to be about decarbonization and the energy transition. More generally, if you just look at technological data about technological performance through time, and I've spent a lot of time staring at curves for technological performance versus time, what you see is that technologies improve at very different rates. And these rates are highly persistent, and as I'll show, this can be used to make good predictions of long-term growth. And to take a step back and motivate this, if I asked, what has been the biggest mistake we've made in thinking about how to make the transition, the energy transition for climate change, it's been people persistently think about what things cost now and not what will they cost in the future using the methods that we have that tell us a lot about what they will cost in the future. So just to make an example, here are some technologies, broadly speaking, over a 20-year span. So we're looking from 1998 to 2018. And we see, on one hand, hospital services, which in the US went up by 225% during that period, college tuition and fees, which went up by a little under 200%. And down at the bottom, we see television, which dropped, once you adjust for quality, by a factor of 20. So we have dramatic differences. And not only are there huge differences, but they're very persistent. Televisions dropped every year. Hospital services went up every year across that period. So this suggests that you should be able to forecast these things, and which is I'm going to say a bit about now. And just because I'm not going to go into too much detail about how we do this, but I want to show you the basis so that you have a feeling for whether it's credible or not. And of course, the most famous forecast is Gordon Moore's forecast, who in 1965 said that the density of transistors and semiconductors is doubling every 18 months. He later shifted it every 2 years. But that forecast has been remarkably accurate up until now. Now, it's starting to fail now, as everybody knew it would, because we're actually reaching the quantum scale, and it can't keep doing what it did for physical reasons. But until that happened, this forecast was remarkably accurate. There's actually an older method of forecasting technological costs due to Theodore Paul Wright. Very interesting character. He managed US aviation production during World War II. He was a World War I flying ace. His brother was Sewell Wright, who was one of the leading evolutionary biologists. His other brother is Percival Wright, who founded political science. But okay, he went into industry and he wrote one paper proposing a law that I call Wright's Law. It's also called a learning curve, which says that costs drop as a function of cumulative production X to some power that's around 0.3. One way you can think about this is every time cumulative production doubles for airplanes, he argued, from a given factory, every time the cumulative production from that factory doubles, the costs for producing that plane drop by 20%. So this is proved to be a remarkably good rule of thumb for airplanes. It also turns out that it's a remarkably good rule of thumb for lots of technologies. The general logic is that the more you make, the more you understand how to make it, you learn by doing, and that brings costs down. Of course, other things factor in, economies of scale, technological change more generally. So this is an imperfect law, but it can work surprisingly well. Here's an example for 4 technologies. Going back to Gordon Moore, it works very well for transistors, actually slightly better than Moore's law. It also works for hard disk drives. It works for ethanol up here in blue and photovoltaics. So now, why do we have Wright's Law? Well, we don't really know. I think we have probably the best paper showing that. In this paper, we simply assume that engineers are capable of throwing darts at a dartboard at random, and once in a while they improve things, and they're smart enough to realize when they've improved things. And we then calculated the rate at which things improve, and we showed you get Wright's Law back. And we also showed that more modular technologies will improve at faster rates. But in general, we don't really understand the real factors behind this. This is my one slide with equations. Apologies, but I just want to make sure you realize how simple this is. This is a very simple equation, which just says that the logarithm of cost, the amount of changes in going from year t to t plus 1, the cost improvement is equal to some constant times the logarithm of the change in production plus some noise term. So this is actually a rewriting of Wright's Law to make it into a time series model, which then was useful because it allowed us to think about the errors. And back to models in general, if you hear a prediction, the first thing you should ask is this prediction any good? Do the authors have any reason that they can convince you that the prediction isn't just bullshit? And you know, in economics, most of the time the predictions are bullshit. But sometimes not, and this is an example where it's not. And we were able to know that because, first of all, we derived a priori what would be the errors in making these forecasts as a function of the free parameters of the technology, namely this parameter here and this parameter here. So we derived a priori what we thought was going to happen, and then we took this to the data. So this is one of the cases, you know, as a scientist, you love cases where you actually make a prediction and it turns out to be right without any fiddling, and this was one of those cases. So we developed a probabilistic method for forecasting. So we're not just making point forecasts, we're making probabilistic forecasts. And we tested this by back testing, by making 6,000 forecasts for 50 different technologies, pretending we were at points in the past. And then we applied this to 3 different scenarios for the energy transition. And just to go a little more into the evidence here, what we do when we back test is we pretend we're at a time in the past. We force ourselves to use a method that doesn't know anything about what happened subsequently. We forecast lots of future dates for that technology, and then we repeat that for all the past dates, and we score different methods of forecasting based on the errors we make. And to pool different technologies, we assume they all follow the same law, this law that I showed you back here. We assume everything follows this law. We also tested other laws. This is the one that came out the best. So we assume the process is the same for everything except for the parameters. And this allows us to make objective forecasts with reliable error bars. Now, so we then applied this to the green energy transition, or the energy transition more generally. We looked at 3 different scenarios, one corresponding to more or less no transition. I mean, the transition's already happening, so you can't have no transition anymore, but roughly speaking, a slow transition of the type that companies like Shell are advocating, and then a fast transition that we argued actually just extrapolates present trends in a reasonable way. So that is we look at 4 key technologies: solar, wind, batteries, and P2X, that is power to something electrolyzers. Like you take electricity, make hydrogen, you use hydrogen to make ammonia, or you can make lots of other fuels instead of ammonia. It's not quite clear which fuel is going to win the battle, but doesn't really matter too much for these trends. And so what you see is that here's the data in black. We're plotting things versus time, and then we roll off of the exponential growth that all of these technologies have been on. These are just blow-ups from my early slide. We roll off that exponential growth in an S-curve, and the difference between these scenarios is the rate at which we roll off the S-curve. So in the no transition scenario, we roll off fairly sharply. In the fast transition scenario, we roll off less sharply across all of these technologies. You can see, by the way, that P2X electrolyzers don't have as long a track record. We project that we're going to stay on the exponential path longer and roll off later because those are not as far down the road. This is also just to give you a feeling for how well would we have forecast using our method these technologies in the past, in contrast to the bad forecast by the IEA that I showed you earlier. You see here the actual data for, say, solar, wind, batteries, and electrolyzers. You see experience, that is the cumulative production for each of these technologies through time. This is what actually played out historically. You see our 95% confidence intervals here. You see the median forecast here, and you can see that in every case, we're well within the 95th confidence interval. The forecast for P2 electrolyzers are less certain because it's a less mature technology, and these forecasts get better in a very predictable way as we accumulate more experience, and the ability to fit these curves gets better. Now, I just want to say a little bit more about what we put into our fast transition scenario. And unlike other models, we weren't trying to argue what the optimal course of action would be. We rather looked at what was a reasonable course of action, what do we think is likely, and what costs do we think are likely to happen under these different scenarios. So this, we think, is actually the most likely scenario based on the data. So under this scenario, we assume the key technologies are solar photovoltaics, wind, batteries, and P2X fuels. We extrapolate existing deployment trends. We phase out fossil fuels over the next 25 years. We assume 2% energy growth in all the sectors. So we require that we're not making sacrifices in providing energy. We're actually providing more and more through time. It just gets cleaner and cleaner. And to deal with intermittency, we use P2X fuels for backup energy storage. We assume 1 month of backup energy storage. That is, that we stockpile enough P2X fuels that the wind can stop blowing completely, the sun can stop shining completely over the whole planet for a month, and we can go on providing power for a month. And we cost that in. We cost in the grid, we cost in everything into this. And now, what do we find? Well, and by the way, we use Wright's law, the stochastic version that I showed you, to forecast the cost, and we use a special case of that for fossil fuels because they have not dropped in cost, and they're very unlikely to do so in the future. And by the way, let me make one more comment about technologies in general. Fossil fuels are an interesting example because they're things we mine out of the ground. And so for reasons that are not well understood, if you look on the USGS website, anything we mined out of the ground, they have 100-year records for 100 different minerals. None of them have dropped in cost by a significant amount, or dropped in price by a significant amount over a century time span. Seems to be a universal rule. Nobody understands it very well. But okay, back to this slide. What we see then so we compare the no transition, the slow transition, the fast transition through time. We look at the investment that we're making in each of these under the different scenarios. So in the fast transition scenario, the blue one here, we start out with the median non-fossil fuel expenditure being here, the fossil fuel expenditure being the colored part, and we see that that blue transition rapidly phases out fossil fuel expenditures, sending them to 0 by 27 and making them very small by 2050. There's a little residual fossil fuel for the hard to decarbonize sectors, but not much. In contrast, okay, the no transition you can see here maintains substantial fossil fuel expenditures, and the slow transition somewhere in between. This plot here shows the probabilistic emphasizes the probabilistic nature of our forecasts. You know, we're not making point forecasts, we're assigning probabilities. And by the way, it was the probabilistic nature that we tested in our tests on 50 technologies. And you can see the difference that the fast transition is the cheapest, although there is still some probability that these other ones might come out cheaper. It's low. And this plot here shows what the mean cost is as a function of the discount rate you assume. And so depending on the discount rate, this is business as usual, that is the no transition forecast here at 0. Depending on the discount rate, the savings depend on the discount rate, but with a discount rate of around 2%, we get savings of about $13 trillion in net present value. So very substantial savings. And here you see emissions from the energy sector and the fast transition as a function of time. Emissions are very close to 0 by 2050, and they're essentially 0 by 2060. Now, what about other models? I mentioned the IEA's bad forecasts. There's a whole general family of integrated assessment models that have also made bad forecasts. Here we see their forecast, the data through time. We see forecasts made by other integrated assessment models. We see that those forecasts are still not in agreement with ours. Here we see the record for all the integrated assessment models we could make in all the scenarios. We looked at almost 3,000 different scenarios. This is a histogram of what they forecast for the price of solar, the price decline for solar between 2010 and 2020. This is what actually happened, which is much closer to my forecast in 2010. And why are these models so wrong? Well, they made a lot of haddock assumptions. Like they said many of them do use Wright's law, learning by doing. They use the deterministic version. Okay, fine. But then they fudge it. They say, well, what they don't like is if they run their models, they would just overwhelmingly go to renewables. So they say, oh, well, there must be something wrong. So they put in floor costs. So there must be some cost below which solar cells just can't drop below that cost. So these green lines show their historical values that were assumed for solar photovoltaic costs. And here you see the price drop, the system cost dropping and punching right through all of their floor costs, as they will continue to do through time with very high likelihood, at least according to our forecasts. This also compares our forecast to other forecasts, again showing that we differ in what's going on. Now, in this talk, I don't want to give you the impression that climate change is just, the energy part of climate change is just a slam dunk. It's all going to fix itself automatically. No, that's not going to happen. There are significant roadblocks. The biggest roadblock, I think, is grid expansion. You can't get solar or wind to the grid, to consumers without going through a grid. To make this happen, we're going to electrify a lot of the energy economy, and we need to expand the grid by roughly a factor of 4 to do that. And that means we will spend a lot of money building up the grid, but that's offset by the fact that we're already spending about $4 trillion a year on energy, and we're going to save enough by making energy cheaper, because energy is going to become cheaper than it's ever been. And we're going to save enough by making energy cheaper that we easily pay for the extra increase in cost of the grid. My son works at the Federal Energy Regulation Commission, and he told me that they have enough renewable projects proposed to more than double the electrical capacity of the US. What's blocking them from approving them? Grid capacity, which requires political will. Okay, and actually I should also emphasize that storage technologies also still need some help. Solar and wind are already at cost parity with other sources, but we critically need better storage, and hydrogen-based technologies in particular deserve continued support to make that happen. We've seen that that can happen with solar and wind. We need to keep doing it with that. Now, I just want to make a comment about people will say, but wait a minute, government shouldn't pick winners. That's not their job, you know. Just put a carbon tax and let the economy do its work. Well, first of all, carbon taxes have shown to be politically very difficult to put in. Portfolio mandates are a lot easier to pass. But secondly, you know, we have another paper looking at technology investment, which is different than financial investment, where, you know, if you went to Finance 101, they teach you that in a portfolio, you should really diversify your investments very strongly. And anything that has a positive, can make a positive return should be in your portfolio to diversify it. But when you're investing in technologies, your investment is affecting the outcome. The investment helps the technology drop in cost. Now, the effectiveness depends on the technology. I hope you've convinced in that. We can invest in nuclear power, which I should have actually said something about, I'll come back, or fossil fuels till we turn green. The prices have not dropped through time. But investments in solar, wind, batteries, P2X fuels, prices do drop as we invest, and we have to invest to bring them down. So if you diversify by investing in everything, you don't make progress in anything. So you do have to make some decisions about concentration. Now, on the other hand, you might be wrong, so you don't want to put all your eggs in one basket. You want to spread your eggs across a few baskets, and you want to make good bets. And this is very easy to show mathematically. Now, I want to close by just saying that my group at Oxford and my company, Macrocosm, which is trying to roll these things out and bring them into practice, we're making alternative climate economics models. Our models are highly modularized, so we model each piece of the economy, which after all, it's the economy that's making carbon emissions. It's not the climate doing it on its own. And so we're trying to model this transition by modeling each piece using this new thing called complexity economics that makes full use of big data and big computing and makes economic models where we use behavioral rules for the agents rather than maximizing utility functions, which makes our models scalable, which allows them to render the economy with much more realism than traditional models. And so we're building these models out a piece at a time. And my company, Macrocosm, is trying to bring these things up to scale. I did forget to mention nuclear. Back to my scenarios from before, we also looked at nuclear. Nuclear is much more expensive than business as usual because, you know, it's a technology whose cost has not come down in 60 years. It's very unlikely to come down in the future, and the other technologies are dropping in cost quickly. So I think it's very unlikely to catch up, and I'm willing to put money on that with anybody that wants to bet. And that is the end of my talk. I'm hoping you have a few questions for me because I think I did manage to end a little bit ahead of schedule. Thank you. Some brave soul.
Remarks or clarification on the cost of the grid expansion?
Yeah. So the grid expansion, you know, maybe just say a little bit more about what we did. We intentionally picked technologies that had a good enough history that we could forecast their cost declines going forward. Now, the grid, we couldn't get data on what, you know, we can get data on what the grid costs now, but we couldn't get nice time series records of what the grid costs through time. So the way we forecast it is you can just calculate how much electricity you have to satisfy the demand, factor 4 above what we have now. And then you can look at what does it cost to install grid capacity now, and we assume that it's not coming down because we were trying to be pessimistic. We tried to bend all of the assumptions in favor of the status quo so that we could defend our estimates. So we basically just assumed the grid costs what it costs now, looked at cases when you can put wires in existing conduits versus when you have to build whole new infrastructure, new transmission towers or underground cabling. But, so that's what we did. And the details are all in the supplementary material to the paper. Yep.
Thank you for your presentation. I have a question. It's nice when you can build a model and pick the elements that are going to be in it, but reality is that there are currently a lot of projects globally to not only find but explore hydrocarbons, some of which have a 20 to 25, 30-year timeline. Sanctioning an offshore oil field takes 25 years to develop, and there are probably 10,000 of those in process. There's a lot of work being done to clean the use of these fuels. So how do you justify that in 25 years there will be no fossil fuels being used, when the reality is that most countries depend on those economies as well?
Yeah. So I didn't say no fossil fuels, just that the usage would be quite a lot lower by 2050. You know, certainly true, there's lots of fossil fuel projects in process. At the same time, it's true that fossil fuel generation and usage has peaked, and we're now significantly over that peak. I think it will come down exponentially as renewables compete. Now, there is another challenge that I didn't go over, which is that as fossil fuel usage drops, well, actually, let me say one more thing. There are a lot of plans that I gave Sally Benson some flack for yesterday to use fossil fuel power generation with carbon sequestration and storage, scooping the carbon out of the smokestack as the smoke goes up the stack. I don't think that's going to be cost effective for two reasons. One is that fossil fuel power by 2030, or by 2050, except as a backup source, is going to be too expensive. And secondly, so it's so expensive that even if the carbon sequestration and storage is free, it won't be competitive. And the operating costs of those plants will increasingly be higher than the cost of installing new capacity. Now, there is one thing that makes me very nervous, which is that as fossil fuel production ramps down, the marginal cost is going to drop. The laws of supply and demand will bring it down. So fossil fuels will become more competitive as that happens. And then there's going to be a question of whether the lobbies, because a lot of this is political. If you look at, say, deployment of renewables across the globe, it's not based on resource quality, it's based on politics. And so will the politics shift as the green energy companies become, as they have comparable revenue to the brown ones, so that they can really challenge it, and we may finally get some, at least in all but Russia and a few countries, we'll get laws that will handicap carbon generation. In my study, all we wanted to do was show a proof of principle that we can actually do a rapid green transition and save money relative to where we are now. I think sorting out the forces of exactly how are fossil fuel prices going to drop, how will that get slugged out, where will there be regulations in place, that remains to be seen. So, thanks.
You mentioned that historically materials costs have remained flat, and these technologies are following the Wright's law to drop in cost. Do you ever see these technologies bump against the material cost, or they form some sort of lower bound as those costs start to drop?
Yeah, it's a good question. So they do bump against those. In fact, if you go back to the solar trajectory, there's a bump in the roughly 2000 to 2010 where costs stopped declining, which was due to high material cost. And, but it was a bump. Then other stuff happened and they came rocketing down again. Material costs started dropping as well. So there have been bumps, and this kind of forecasting doesn't forecast, there's always a detailed story that makes all the wiggles happen. We're not forecasting that, we're just forecasting the broad declines. Materials, traditionally, one should also worry about material shortages, but traditionally, material shortages have usually been circumvented by substitution. People find other ways of doing it. I'm confident with solar photovoltaics, for example. We currently use polycrystalline, but there are perovskites that look like they may be even better and don't use rare earth materials. So I'm pretty confident that through time innovation, we'll sort that out. I want to stress that details of innovations are not predictable, at least we haven't figured out how to predict them. What is predictable is the rate of improvement for technologies in a given class. So we can't predict what the innovations will be, but we can fairly well predict what the costs will be in the future.
Thank you.
Thank you.
Well, thank you very much for just an amazing presentation. I have not seen anyone who can explain very complex and sophisticated models so well that I can get the whole picture. So thank you very much.